Hello everyone. Today we are in fifth session of this crash course series. We are going to deal with isomerism part 2. In part 1 we talked about what are isomers and what are the classifications of isomers, what is structural isomerism and further classifications, and we saw about what are stereoisomers and their classifications. In today's session, we are going to deal with what are optical isomers and how to calculate the number of optical isomers from the given molecular formula. And also we are going to see optically active compound with no asymmetric carbon and racemic mixture and meso compounds, and finally we are just going to see the overview of conformational isomers. And most importantly, we are going to solve some problems from previous year papers. So don't miss out this session. I'll be explaining each and every part in detail, and we are going to solve problems to master in isomerism. Without any further delay, let's get started. What is optical isomerism? We all know it comes under the category of stereoisomerism. Stereo means difference in spatial arrangement, right? Optical isomerism is a form of stereoisomerism where the molecules have identical molecular formulas and bond connectivity but differ in three-dimensional spatial arrangement. Most importantly, it results in non-superimposable mirror image. Okay, so if you are matching those mirror image, it will not match. That is what the non-superimposable mirror image is. Okay, so that is what optical isomerism. The molecules are the compounds which exhibit this property. Those are called optical isomers. Okay, so without getting much detail about it, I just want to give you the terms we are using to explain this optical isomerism. Okay, the first term, that is chiral carbon. Chiral carbon, asymmetric center. These two are the different words. Chiral carbon are the carbon atom which is attached with 4 different molecules or atoms. Say for example, I am having carbon attached with hydrogen, iodine, fluorine, and another side CH3. 4 different groups are attached with carbon, that is chiral carbon. This is mentioned as star, asterisk symbol. Okay, and this is called stereo center or asymmetric center. More importantly, asymmetric means if the property, if the carbon or the compound is lacks of symmetry. There are different types of symmetry: plane of symmetry, axis of symmetry, center of symmetry. We are going to see about that. Okay, if a compound lacks these symmetric property, then that becomes asymmetric. Those are called asymmetric carbon or asymmetric center. Okay, here this carbon is asymmetric carbon. Our next part is that optical isomers. Optical isomers are the molecules which can rotate the plane polarized light. What is plane polarized light? That is our normal light, white light, which is having vertical and horizontal waves in it. Okay, so which will be looking like, let's say this is the plane. It would be better if you are imagining it in three-dimensional way. The vertical lines and the horizontal waves as well, in case of our normal light. But in case of plane polarized light, we are producing it. through passing the white light into nickel prism and polarizer to make it as a singly arranged waves. Waves are in only one direction. Okay, that is plain polarized light. So if an isomer exhibits optical isomerism, then it can rotate the plane polarized light either clockwise or anti-clockwise. If that is rotating in clockwise, then that is called d-isomer, also denoted as plus symbol. Okay, if that is rotating that as an anti-clockwise, then that is L-isomer, denoted by minus symbol. Okay, so which can rotate plane polarized light to clockwise, that is D-isomer, which can rotate plane polarized light to anti-clockwise, that is L-isomer. This much clear? Yes. I said the word rotate. So rotation means the angle changes, right? So how much it is getting rotated? Let's say I am using a molecule tartaric acid or any optically active molecule. How much rotation is happening, either clockwise or anti-clockwise? That rotation we are talking about here in case of specific rotation. It measures the optical activity. And how it is calculated? Specific rotation is alpha, and this is calculated by alpha L into C into 100. Alpha by L into C into 100. Here alpha is observed rotation when we are passing the molecule into plane polarized light, and L is the path length in decimeters. C is the concentration of the solution. Okay, this rotation is observed using a polarimeter, that instrument, and it can be of positive textorotatory or levorotatory. This kind of question can be asked to apply this formula. They will give you observed rotation, path length, concentration and all. They can ask you find the specific rotation. Okay, so that kind of question can be asked. Let's move on to the next part, that is types of stereoisomers. Types of stereoisomers, we talked about optical isomers, we talked about conformations. Here, enantiomers and diastereomers. What are these? These are very simple. That if that is an enantiomer, then the molecules are, the mirror image of that molecule will be non-superimposable. Non-superimposable mirror images are called enantiomers. They'll have identical physical properties. Physical property means color, smell, what we can observe it without doing a reaction, and those parts of physical properties, they will have identical physical properties except the rotation of plane polarized light. It can be of D or it can be of L, and interaction with their other chiral molecules. How it will interact with other molecules. What is this word chiral over here? Chiral means the same. I told you, right? Stereo center or chiral center. Chiral means a carbon which is having 4 different groups attached to it. And enantiomers will have equal and opposite specific rotations. D and L pair are considered as enantiomers, but they should be of mirror image and non-superimposable. Talking about diastereomers. Diastereomers are the stereoisomers which are not mirror images and not superimposable also. They are neither mirror images nor superimposable. They'll have different and chemical properties entirely and can occur in molecules with multiple stereocenters. They can have multiple, more than one stereocenters. We'll see the example. For example, if I am taking a molecule like this, HCl, HCl, C2H5. What about the mirror image of this molecule? Once again, this will have CH3, C2H5 will be on the same position. Cl will come here, H will be here, Cl and H. These are mirror images, but is it superimposable or non-superimposable? For example, if I am taking this molecule and trying to match with the original one, is that matching? No. Cl and hydrogen are in different positions, right? So, which means that it is non-superimposable. Okay, so these two are enantiomers. Enantiomers. It can be of D and El. Talking about diastereomers. For example, if I am taking a molecule, let's say I am taking the same molecule and a pair of this diastereomer will be there shouldn't be a mirror image, right? So it can be like this. So these are not mirror images, and as well as these are not superimposable also. They are diastereomeric pairs. Okay, if examiner gives you a molecule, check with these conditions and put the right answer, whether that is enantiomer or diastereomer. Now we are going to see the next part, that is elements of symmetry. We have different symmetric properties. As I told you earlier, what is asymmetric center means? If that lacks of symmetric property, then that is asymmetric center, right? Asymmetric carbon. What are those symmetric properties? In general, we have these three important symmetric properties, that is plane of symmetry, center of symmetry and axis of symmetry. Plane of symmetry is very simple. Let's say I am taking a molecule which is having two stereogenic center, let's say, and I am having these H. So from here, these two are mirror images to each other, isn't it? So this is mirror image. So both the sides we can see the same molecule. That is plane of symmetry. If we divide the molecule into two identical halves, the mirror image relationship between there in this compound, right? This is plane of symmetry. Although the four different groups are attached to the carbon, since that is having a plane of symmetry, this compound is not optically active. Okay, and the second one is center of symmetry. Center of symmetry means from the middle line, how the symmetry occurs. For example, if I am taking a molecule like this, The simple molecule, let's say I'm taking a simple CO2 molecule, or simple CH2CCH2. Okay, so here I'm having central carbon, and both the sides from this point I'm finding the same compound, same molecule attached to it, and another side also I'm finding the same molecule. So which means that is having center of symmetry. Okay, so that is one symmetric property. And the third one, that is axis of symmetry, means if I'm rotating one side of a molecule, I should get the same thing. Let's say the simple molecule, I would say that is H2. Okay, let's say I'm HA and this is HB. I'm naming it, these hydrogens. So I'm rotating it on one side. It will become HB and HA, isn't it? Once again I'm rotating it, I'll be getting the same molecule again. So the rotational axis that produces the identical arrangement multiple times per 360-degree rotation, then that is having axis of symmetry. Why these are important means, depend on this we will find whether the compound is optically active or not, whether that compound exhibit optical isomerism or not. Okay, so this is some basic thing. Mostly they will be asking questions from plane of symmetry. We applied this concept in another compound, that is called meso compounds. Meso compounds are the one which are having chiral center, but that is optically inactive because of the cancellation of optical activity, that is because of plane of symmetry. Okay, the same example as here, I'm taking tartaric acid. So this is having a plane of symmetry, right? That's why it makes this compound optically inactive. That is which very much important. Meso compounds are optically inactive, although they are having chiral centers. But what if that is having odd number of chiral center? Optically activity may come, but this is common when the even number of chiral centers are there, even number of stereo centers are there. Okay, and finally another term, that is racemic mixture. Racemic mixture is nothing but, we talked about D and L isomer, which can rotate clockwise, that is D, and which can rotate anti-clockwise, that is L, LIBO and textorotatory, right? So if a compound that consists of both the mixtures, both the compound or both the isomers together, that mixture is called racemic mixture, but that should be of equal amount. Let's say if I'm having 50% of D isomer, then I should have 50% of L isomer. The equimolar mixture of D and L isomers are called racemic mixture. Okay, and what will happen to that optical activity means, it will become optically inactive because of external compensation, which means D isomer is plus isomer that rotates on one side, L isomer is minus isomer that rotates the plane polarized light to another side, which will cancel out each other, right? Racemic mixtures are optically inactive because of external compensation. Meso compounds are optically inactive because of internal compensation. Clear? Now let's move on to how to find number of optically active compounds in a or optically active isomers in a given molecular formula or given structure. Okay, there are three different formulas we have. these different possibilities we have. The first one is unsymmetrical molecule. It is not at all having any symmetry in it. No plane of symmetry, no center of symmetry, no axis of symmetry. Then you can use the formula of 2 to the power n. N refers to chiral center. It can be of any number of carbons. 2 chiral center, 3 chiral center, 10 chiral center. It can be of anything. So, a number of optically active isomers become 2 to the power n. And out of this, which is mesoform, we said that is not possible over here. They are unsymmetrical. And the racemic mixture becomes A by 2. Which means if I am getting 10 optically active isomers means 5 will be racemic mixtures. The total isomers are A plus M, that is 2 to the power n only. Okay, the second case, that is symmetrical molecules with even number of asymmetric carbon. Even number means 1, 3, 5, 7, etc. In that case, you have to use the formula. The total optically active isomers are 2 to the power n minus 1. Once again, n is for chiral center. The mesoforms will be 2 to the power n by 2 minus 1. And the racemic mixtures, which is A by 2, total isomer A plus M, optically active isomer plus mesoforms. And finally, the third category, that is symmetric molecule with odd number of asymmetric carbons like 2, 4, 6, 8 and etc. In that case, optically active isomers would be 2 to the power n minus 1 minus 2 to the power n by 2 minus 1 by 2. Okay. Here this part belongs to meso compound and total isomers become 2 to the power n minus 1. Okay. So kindly take the screenshot of these formulas. This will be very useful while you are solving this kind of problems. Okay. Then we are moving on to optical activity without asymmetric carbon. You said it should have a chiral carbon, it should have an asymmetric center. But how a compound can exhibit optical activity without having those centers? Yes, that is possible. Those molecules are allenes, spirenes, biphenyl with restricted rotation, some metal complexes. Here, these names are important. Okay, I'll give you the structure. So, if an examiner is giving you the structure, then you won't be able to answer this question if I am not giving you the structure. The first one is allenes. You can see it is having CCC in the middle, 3 carbons, and A and B, the different molecules or atoms are attached. Here, how it becomes optically active? The first thing is, it is having a double bond in between, and these double bonds are arranged in the way perpendicular to each other. The 3-dimensional way, I should write it like this. Can imagine this carbon is perpendicular, it's towards you. This B is away from you, A is towards you, and these two are in the plane. It takes out a different 3D arrangement. That's what the optical isomers are. Right. So that makes allenes with odd number of carbons become optically active. What will happen to even number of carbons in allenes? Then that will become optically inactive, because that will get cancelled out each other, compensation happens, that becomes optically inactive. Okay, the next example is pyranes. Pyranes are nothing but replacing the double bond with the spiral structures, like replacing it with this kind of structures. And biphenyls with restricted rotation. Say for example, here I am having biphenyl CH2 S double bond O, another phenyl ring. So these are having biphenyls, but the carbon that becomes optically active because of the tetrahedron shape, because the attached groups are different. Some metal complexes, we'll see that in coordination chemistry chapter. Point to be noted here is allenes, pyranes and biphenyls are optically active even though that is not having asymmetric carbon. Then we came to and last part of this session, that is conformational analysis or conformational isomerism. Here I just want to give you the important points to be noted. The first of all, conformations is due to the rotation around the single bonds. There is no work for the double bond, triple bond sections. Only the rotation due to the single bonds. Okay. Say for example, I am taking ethane. CH3, CH3. Is there any double bond? No. Is there any possible rotations? Yes. I would like to represent it like this. With this is front carbon and circle is rear carbon. We saw that in last class. Sorry. H, H, H. There are two types of arrangements over here for this conformations. I mean, there are two types of conformations we can have for ethane. One is that staggered, another one is eclipsed. This conformation is called staggered, and the eclipsed will be look like this, which is having the bond angle or dihedral angle between the atoms will be very less when we are compared to staggered. Out of these, which will be more stable? Staggered will be more stable than eclipsed. Okay, because in case of eclipse, the repulsion can happen, which makes it less stable than the other conformation. Similarly, you can draw that for butane as well. Butane CH3, CH2, CH2, CH3. If you want a detailed analysis of butane, let us know. Here the front and rear carbons to be taken in these two carbons. Okay. The one of those conformations will be looking like this. Here, both in staggered and eclipsed, we do have other arrangements as well. I'll give you the most stable conformation of butane, that is anti-conformation. Both the CH3 groups are opposite to each other. The anti-conformation, which is more stable in case of butane. Other conformations are fully eclipsed and gauge, partially eclipsed. Those will be there, but out of those, anti is more stable because both the CH3 groups are opposite to each other or anti to each other, so the repulsion or the dihedral angle will be very less, which makes it much more stable. Then cyclohexane. Cyclohexane means what? Ring which is having 6 carbons, right? So this type of arrangement, this type of structure for cyclohexane is much more congested, much more strained. For that we can write it in different way. Out of one way is this, which is called boat and chair. This is chair and this is boat. Out of these two, which is more stable? Chair conformation becomes much more stable than boat conformation because it eliminates the axial and equatorial bond strain and repulsion, and those stuffs are there. This part we can go in detail, but it will take more time. It involves lots of concept. So I want to make it short. I just want to tell you, chair conformation is much more stable than the boat conformation. That those kind of questions only we can expect from JEE Main and NEET. Okay. So by this we just finished the theory part. Let's see whatever we have learned, can we solve those questions through this? Okay. So the first question is about which of the following compounds will exhibit geometrical isomerism? The option A, 2-phenyl 1-butene. Quickly we'll draw the structure. 1-butene and 2-phenyl. And 1,1 diphenyl 1-propene. This is A. B is 1-propene 1,1 diphenyl. And C is 1-phenyl butene. 1-phenyl 2-butene. 1-phenyl 2-butene. And D, that is 3-phenyl 1-butene. 3-phenyl 1-butene. Okay, so out of this, which can exhibit geometrical isomerism? You can see it should have two different groups attached with single carbon, and it should have a double bond in it, right? Let's take option A, that is having 2 hydrogens over here. That makes it optically it is not exhibiting geometrical isomerism. And if I'm talking about these phenyl group, then surely that is not. And what about this one? Yes, it can. So let me write it in this way. Carbon which is attached with one hydrogen, another CH2, phenyl, double bond, another carbon with hydrogen and CH3. So this can exhibit geometrical isomerism. What about option D? That is not, because of two hydrogens over there. So the right answer is option C. These are previous year questions and anticipated questions for this year. Okay. Then number of structural isomers for C6H14. Structural isomers. So first write the molecule and then find out what are the different ways we can write it for this. Okay, so this is number 1 and number 2 is, I can put CH3 in the middle. CH3, CH2, CH2, CH3. Third configuration, I can write it with isomers. I can write as CH3, CH3, CH2, CH3. And the fourth possibility can be CH3, CH3, CH, CH3, CH3. And the fifth possibility, that is CH3, CH2, CH3, CH2, CH3, H. Is it possible that the name of this compound will be 1, 2, 3, 4, 5. So second position I'm having, third position I'm having methyl. Here I'm having it in second position. Here 2, 2. Here I'm having it in 2, 3. So these are the 5 possibilities I can write for structural isomers of C6H14. Let's move on to this question, which is asking about absolute configuration of this structure. Here I am having 2 carbons. Let's say this is 2 and this is 3, because we should start naming it from functional group. Okay, so let's do the absolute configuration of carbon 2. That is, it starts from OH, then it goes to Cl, then COOH, finally hydrogen. So hydrogen, which is in above the plane, which is in horizontal position, we have to do the reverse of whatever the result we are getting. So first of all, 1, 2, 3, 4. So which makes it clockwise and R. So I have to make it as yes. So 2, yes. Then the third one, I'm numbering it different color, 1, and this becomes 2, this is 3, and hydrogen becomes 4. Once again I have to do the reversal. This time this is going 1 and 2, that is anti-clockwise, which is S. Doing the reversal, that becomes R. So 3 R 2 S, that is the answer. Then next question. Acetone and propanol are what kind of isomers? Acetone, which is having keto functional group, propanol, that is aldehyde functional groups. So these are functional isomers. Then number of optical isomers of the compound. CH3 CHBr, CHBr, COOH. So how many optical isomers this compound is having? Obviously this is not having any meso compound. Okay, so this is having 2 chiral centers. So optical 2 chiral center, and is it symmetric? No, is it not? It is asymmetric. So apply the formula 2 to the power n. So n here is 2. So which makes the answer D. Let's solve this question. Total number of acyclic structural isomer possible for the compound of molecular formula C4H10O. Okay, we should not include any rings. Okay, so let's start writing it. This is 4 carbon system. So CH3, CH2, CH2, CH2OH. So number of carbons are 4, number of hydrogens becomes 7, 7 plus 3, 10. And the second way of writing it, which is, you can put the functional group in second position. CH2, CH3. The third way, it's giving the substituent at different position. CH2OH. Fourth way, I can write it in the way of 3-degree carbon. And the fifth way of writing it will become the different functional group. Is it possible? We know the functional isomer of alcohol is ether. So let's try out that way. CH3, CH2, OCH2, CH3. How many carbons? 4. How many hydrogens? 10. And 1 oxygen. Okay. The next way, let me write the different isomer of the ether. It is the metamer of this ether. And the another metamer is kindly check number of carbons and hydrogens are sorted. Yes. So these are the possible acyclic without any ring. I can write the structural isomers of this molecular formula, that is 7. Now let's move on to the next question, that is asking for meso compounds do not show optical activity is because we know not very well, right? They do not contain chiral carbons. Yes, they do have. They have non-superimposable mirror images. They contain plane of symmetry. They do not contain plane of symmetry. They contain plane of symmetry. So that is the answer for this question. optically active molecule is among these four? So let's analyze it one by one. Is it optically active? No. This is having planar symmetry. This becomes meso compound. So this is not. And what about this? This is also not because of plane of symmetry. And what about this one? Here you can see COOH and COOMe. So which makes it different? And final compound that is also exhibit optical inactivity. So the answer to this question is option C. What I tell you is do as many as problems you can, try to do more questions, come up with different ideas to how to solve the questions. That will give you deeper understanding about the concept rather than studying the concept. Okay, so practice more because practice makes a man perfect.